Okay, so we're going to continue talking about vibrations and waves. Next Wednesday, I'm going to bring my guitar and amplifier in. So if anybody wants to bring anything they want to demonstrate, musical wise, we're not going to be completely done with sound at that point, but we may be starting to talk about it. And we'll definitely talk about waves on strings, which is what guitars, how they operate. Before we move, so what I'm going to do first, just talk about some of the courses. So we're spending 2 days on vibrations, but mechanical engineering, aerospace engineering, um, physics, waves are important. So you might take a whole class on waves. Vibrations. This is called Theory of Vibrations. Obviously, it's an old book, but they still have the class now. Things still vibrate. And the kinds of things they talk about are oscillatory motion. Okay, we've kind of talked about that. Free vibration. Free vibration is where you have something that's oscillating, but you're not inputting any kind of force. You just start it going and it oscillates. So what I did last time in class, where I started if I didn't shake the spring at all, then that would be free vibration. And typically that's just a sine wave, and it dampens down, the amplitude gets smaller and smaller as you time goes along. So that's free vibration. The next topic is harmonically excited motion. So that's if I was going like this with the top of the spring, I would be inputting a force into the system. Transient vibration, that's kind of like if you hit a tuning fork and it goes bing and it drops off. So it's just a short term kind of thing. And then they get into more complicated stuff. 2 degrees of freedom systems, multiple degrees of freedom, lumped parameter systems, continuous systems, Lagrange equation, random vibration, nonlinear vibration. What we've been dealing with is linear vibration because force equals k times x. It's proportional. It's a linear relationship, but let's say whatever was causing the restraining motion was not linear. So that's one book you take. I can't remember if that was an elective or whether that was a required. This was definitely required. It's called The Analysis and Design of Dynamic Systems. And if you look in here, you'll see things in motion. So anything that's in motion in a repetitive manner, like car engines that are rotating or anything that rotates or reciprocates, can result in vibrations, and you have to analyze the system so that you make sure that they don't have any issues with having the vibrations get so big that the thing falls apart. So even aerospace engineers, they're going to have wings that are fluttering like this. So, those are vibrations. You've got the engines that are rotating. If you've ever flown in an airplane and you're on takeoff, sometimes there's certain times that you feel like there's a bigger noise from the engines. You hear this, and then it'll kind of dampen off. And what that is the the vibration. You're rotating the motor at a certain speed, and if that speed has some relationship to the spring mass behavior of everything that's connected to it, then you can end up with harmonics, and you just want to make sure those harmonics are not so big that the plane falls apart, or not, the thing connecting the engine to the wing fatigues and falls off. So those are all important things. So vibration is an important thing. The math's pretty heavy compared to some of the other. That's why I think people struggle with those particular classes. It's a little more math heavy. Okay. What I wanted to do first is to derive the equations for a pendulum. We talked about a pendulum, so I just wanted to go through the process of how you come up with this. We did it for the spring mass system. We knew that the force was equal to negative kx. We put that in there. That was the force. And we had mass times acceleration, which was the second derivative of the position with respect to time. But let's draw a pendulum here. So we got something holding the pendulum. We got a pendulum. It's going to be off center just a little bit. I'll put a little weight at the end of it. We'll assume that the weight of the rod is negligible. And we'll draw a line here, which is the center line of the whole situation. So what we're doing here is we're actually going to sum torques around this point instead of summing forces. So you've got this is the length, that's the distance from this point of anchor to the center of the pendulum. And the forces acting on the pendulum there's two forces. There's the force due to the weight of the object. So this is the weight. And the weight is equal to the mass times the acceleration due to gravity. And what you can do is you can break that up into two components. You can break it up into a component that's in the direction of the pendulum arm, and one that's perpendicular to that. So I'm going to call this thing F sub n, which is the normal force, and we'll call this F sub t, which is the tangential force. And those add together to give the weight. I mean, maybe I should do W instead of F, sorry. Hopefully you didn't get to that point yet. So you got W sub tangential and W sub normal. So we can find, how these relate to the weight by knowing this angle here and this angle here are the same. So we'll call that theta. So this little angle is theta. So if we want to find W sub t, the tangential weight component of the weight, it's the opposite side from the angle. So that's going to be equal to W times the sine of theta. And the normal component of the weight is W times the cosine of theta. And you can see when theta equals 0, this tangential component should be 0. And if you plug 0 into here, you're going to get 0 because the sine of 0 is 0. So if we do the sum of the torques around this point 0, that's equal to the moment of inertia times the angular acceleration. Now, the only force that we have acting on this, which is actually going to cause a torque, is this tangential component. This normal component, you can see, goes straight. If I take this and I project it right up here, it goes straight through point 0. So we can say W sub n contributes no torque around 0, the point 0. And remember, torque is equal to force times distance. So in our case, the force is W sub t, the tangential component of the weight. And it's going to be negative because this is positive theta, and this is pointing in the direction of negative theta. So this is pointing in the opposite direction that we are. When we go positive theta, this is going to be pointing in negative theta. If we go on the other side and we have negative theta, if we go this way, if we let theta be 0 here, negative theta is going to give you a push in the positive theta direction. So you got a negative sign, just like we had force equals negative k times x. So it's W sub t. The distance is the length. So that's the torque. The moment of inertia is equal to the mass of the object times the radius squared. We consider this to be a point mass. So that's the moment of inertia for a point mass. And the radius is L. So we get L squared. And alpha is equal to d squared theta dt squared. It's the rate of change of the angle with respect to time. second derivative. So if we plug all those in, we'll get the torque, which is negative W sub t times L is equal to the moment of inertia, which is L m times L squared times d squared theta dt squared. But W sub t was equal to W times the sine of theta, and W is equal to the mass times acceleration due to gravity. So I can plug that in here, and I get negative mg sine theta L is equal to m L squared d squared theta dt squared. See, the masses cancel out. We can divide by L. So we get negative g divided by L, because if we divide by L squared, we'll have L squared, L divided by L squared, which is 1 over L. So we get g over L times sine of theta is equal to d squared theta dt squared. And if we put it in kind of a differential equation form, we'd have d squared theta dt squared plus g over L sine theta equals 0. So that's the second order differential equation, but it's not linear. If you remember back to the spring mass system we had, so this is spring mass, we got d squared x dt squared plus m, is it m over k or k over m? K over m. K over m times x equals 0. So you can see they're very similar to each other in their form. This one's a second order differential equation. It's linear because we just have x. We have k over m. Here we have g over L. So that's why I mentioned last time, or sometime, maybe Monday, was that if you let theta be approximately small, so let theta be small, and at that point, the sine of theta is approximately equal to theta. You know, we've shown that many times. The squeeze theorem, if you plot those two functions, you'll see as theta gets close to 0, the sine of theta is close to the x value. So if you make that substitution, you get d squared theta dt squared plus g over L times theta is equal to 0. Now the result of this equation was that the solution, x as a function of time, was equal to some amplitude times the sine of the square root of k over m times t. And so the same thing would happen here. You would find that theta as a function of time is going to be some theta max. So maximum, this would be the amplitude, this is the amplitude, and you'd end up with the sine of the square root of g over L times t. And then over here we said 2 pi f is equal to the square root of k. For that to work, the frequency has to be related to this ratio of the square root of k over m as such. So frequency is equal to 1 over 2 pi times the square root of k over m. So over here, the frequency is going to be 1 over 2 pi times the square root of g over L, or the period is equal to 2 pi times the square root of L over g. Just take the reciprocal. Same thing over here. Period is equal to 2 pi times the square root of m over k. So in the lab on Wednesday, we showed that if we increase the mass of the system, I did start recording this thing, didn't I? I'm out of practice here. Okay, so you know, in the experiment, our computer experiment, we saw that increase in the mass, and Aish also demonstrated it. Increase in the mass increases the period, slows down. Increase in the spring constant makes it spring quicker. So the same thing's true for a pendulum. The period gets longer with the longer with the longer arm, and it gets shorter with the higher acceleration due to gravity, which we showed that as well in our little experiment. So that's the derivation. There's a little bit of calculus-based stuff that you get for free. At least you guys are not taking calculus-based physics. Okay, so that's all I have to say about that. Before we move on, one more thing before we move on to waves. So we said for spring mass system that the displacement was equal to x max times the sine of the square root of k over m times t. So if we wanted to know what the velocity was, all we'd have to take, and again, here's another little calculus-based stuff for you. So you take the derivative of the position with respect to time. So the derivative of the sine is the cosine. Use the chain rule, so you'd get x max times the square root of k over m times the cosine of the square root of k over m times t, or we could use frequency. It'd be x max times the frequency times 2 pi f. Square root of k over m is equal to 2 pi f times the cosine of this. And if you wanted the acceleration as a function of time, you take the derivative again. And so the same thing would happen, except you get a negative sign, because the derivative of the cosine is the sine, negative the sine. So you still get x max times 4 pi squared f squared times the sine of the square root of k over m times t. So that's one thing about, now that you know the motion is periodic, you can figure out the velocity as a function of time. And what's that? You can also look at the maximum velocity is going to be equal to just this part right here, the amplitude. So the maximum velocity is equal to x max times 2 pi times the frequency, and the maximum acceleration is going to be x max times 4 pi squared f squared. Again, because this is the amplitude. So one thing you see, we saw this yesterday or the other day too, was the further if you stretch the spring more with the same spring constant, same mass, I said the frequency didn't change, but what happens is the maximum velocity increases. So the velocity to get through a larger distance in the same amount of time, you're going to have a higher velocity. And you can see how it's reflected in this derivative in the calculation of velocity. This part doesn't change if you've got a fixed mass and a fixed spring constant. But as you increase the stretch, the maximum velocity, which is right in the middle of the oscillation, velocity is 0 here, it's 0 here, the max is right in the middle, it's going to increase in proportion to the amount that you originally stretch the spring. And the maximum acceleration happens at the peaks. So the maximum acceleration happens here, it's accelerating this way, and down here the maximum acceleration is at the bottom. And so you get the maximum displacement and maximum acceleration here, you get the maximum velocity here, you get zero displacement and 0 acceleration. Down here you get the maximum displacement and acceleration, but 0 velocity. And you can show that all mathematically from the fact that we showed that this was the solution of the differential equation for motion of a spring mass system. Okay, so that's it for vibration. That's it for vibration right now. Now we're going to talk about waves. So first thing we're going to do is just talk about the different kinds of waves. So we got the slinky, which is one way. Unfortunately, the slinky doesn't. If it would be great if it was zero gravity, because we could demonstrate this much easier. But I'm going to try to. There's two kinds of waves, and I'll write down the answer. I'll write down the names in a second. So Emily, you can hold on one end of this, and we're just going to set it on the desk. You're just going to make sure this thing doesn't. Okay. So one thing you have, except for light waves, you have to have some kind of medium to transfer the waves. But you've got what are called longitudinal waves, and those are waves that are in the direction. And now, so you can see how this energy is transferred along because of the fact that it's on the desk. It gets dampened out, but it just doesn't go far enough. It gets, maybe if we get close, get a little bit closer. Yeah. So you can see how the energy is transferred from here to there without, we're not moving, ultimately we're not moving the medium. We're just moving the energy by, in this case, the spring is stretching and unstretching, and it propagates down the spring in this case. But if you had a sound wave, the same kind of thing applies. What you're doing there is you're oscillating the diaphragm in the speaker, and that's going to oscillate the molecules near the speaker, and that's going to create high and low pressure pressure waves, and it's a pressure, so you get regions of high pressure and low pressure. High pressure is a relative term because it's not really that high a pressure, but that fluctuation in the pressure gets transmitted through the air, propagates through the air, and then it hits your eardrum, which then that pressure variation is sensed by your eardrum, and then that is turned into electrical signals, which goes to your brain and tells you it's a sound. Okay, so this is a longitudinal wave. So sound waves, slinky waves. Sound waves is the biggest example of longitudinal waves. Yeah. Okay. These are easy to get tangled up. You try to do it this way and go. So I'm not going to use it for that. Okay, so let me write that down. Longitudinal waves. Longitudinal waves. So I'm gonna kind of say this is the x direction, and what you'd have is you'd have regions of compression and regions of expansion and regions of compression and regions of expansion and regions of compression, whether that's air or that's a spring. And associated with this, you would have what's called the wavelength. So the distance between regions of high pressure or high compression would be called the wavelength. So lambda is the wavelength. And if you plotted pressure as a function of distance at a particular point in time, I probably should have, let me move it down here. And we'll draw some kind of a horizontal line here. So this is atmospheric pressure. What you'd see is something like, make sure I get this right. Trying to coincide the peak. What I'm trying to do is match the peaks here with the peaks in the pressure. So this would be atmospheric pressure. And then you'd have the small pressure variation superimposed, both plus and minus, on the atmospheric pressure. So you can think of it as a compression wave, compression tension wave. So but that's the, you can, but anyway, the wavelength is the distance between the peaks. We did that again in lab in electricity. the wavelength was 1 over the frequency. So we used the frequency to calculate the wavelength. But if we had gone in and measured the distance between the two peaks for a given wave, we would have found that they matched up exactly with what we came from theoretically. Okay. The second kind of wave is, didn't mean to do that, is called a transverse wave. So let me write over here, sound, slinky. Okay. Examples of transverse waves are like ocean, strings, light. So these are all transverse waves. So Emily's going to help me out again here. So here we have a string, and you put some tension on the string like this. And so what I would do is, instead of pushing it this way to create energy, I pull the string down, and then what happens, and it moves pretty quickly, so it's harder to see. But this tension in this additional tension in the string beyond the kind of equilibrium tension, what that does is it causes a force here, and that what's going to happen is this wave is going to propagate down the string, but the variation is this way, not this way, but it's up and down. It also gets dampened out. But if I do this at a certain frequency, you can see if I do it slow, nothing happens. But then as I increase my frequency, there's some frequency here where I get what's called a standing wave. If you guys, I'll move around here so everybody can see that. So that's called a standing wave, because it looks like it's just sitting there. It's just going boom, 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 boom. It's not traveling, even though in reality it is actually traveling. Now you can, if you do it fast enough, which I can't do it fast enough, you can actually get, my arms are going to fall off. So you can get where it goes like this and then like that. And we'll do that in lab next week as well. So that's our, people always have fun with that. So what we'll do is we'll connect the two ends of this string to some rods, and we'll take a speaker that will vibrate this much faster than I can. You can almost see it there. I'm starting to get it. Notice there you got about three lobes here. I guess I can move my little finger a lot faster than I can move my whole arm. But what we'll have is this thing will be excited, and we'll be able to relate the number of lobes to the frequency, and we'll see there's some relationship. But those are waves on strings, and the same thing happens for light waves. And also for, what did I say the one with? Strings, ocean waves, yeah. So you get those things. If you've been to the beach, it just lifts you up and lifts you down, lifts you up. Of course, when it gets to the shore, it breaks. But if you go out far enough, you just get lifted up and down. You don't actually get carried away. If you get carried away, it's because it's due to rip currents, not due to the waves that are doing it. It just kind of lifts you up and down. Okay. So we'll draw a picture here of a transverse wave. So it actually does go up and down. It's not just the graph that goes up and down, but the actual object goes up and down. So I'd excite it on this side. And again, the distance between corresponding peaks is called the wavelength. And the wavelength, as the name implies, has units of meters for both of these. Now, we used this before when we were talking about light waves. So when we talked about light waves, we had that the speed of light was equal to the frequency times the wavelength. And normally we cover this after we cover this, but I did it out of order because I wanted to cover electricity and magnetism before I started talking about this stuff. So this is for light. where c is equal to 3.0 times 10 to the 8th meters per second. F is the frequency in hertz, and lambda is equal to the wavelength in meters. Well, for all other waves, V is equal to F times lambda. So the definition for F and lambda are the same. V is just the wave speed. And the units are meters per second. So the question is, for these different kinds of situations, what affects the wave speed? Well, for strings, we'll find out it's a function of the tension in the string and the mass per unit length. So when I bring my guitar in, we'll talk about that. For light waves, it's just dependent upon Einstein, right? Or Maxwell, I guess James Clerk Maxwell. Maxwell's equations, he came up with the speed of light. So this comes from the relationship between magnetic and electric fields. In sound, it's a function of the temperature of the air. So the higher the temperature, the higher the speed of sound, and the lower temperature, the lower the speed of sound. Okay, let me pull up a demo here. PHET simulation, just to kind of talk more about what's going on here. Demonstrate it for you. Google. I don't know what. I'm not sure why they use a wrench. That seems like an overkill situation. So what I have in this case is I have a wrench which I can move up and down, and I have a clamp, which means that I fix the other end's fixed. There are different versions of this, which I'm going to use here in a second. First I'm going to use the loose end, not the, actually no end. Okay, so that just goes out the window. And we're going to use we're going to oscillate it. And we're going to take the damping off so there's no friction. And we're going to slow it down. So what's happening is I'm inputting a displacement on the left, and that energy is being transferred as a wave to the right. And because there's no reflection and there's no damping, it just keeps going forever, wherever the end of the string is. Now, if I stop this like that, it's a sine wave. And it's a sine wave because if you've got this thing rotating in a circle, and this thing's attached to it so that it oscillates up and down based upon the y coordinate of this little dot. So when the dot's down at the bottom, this is at the minimum displacement. And when the dot goes to the top, so let me just move it to the top here. Okay, so there it's almost to the top. So it's at maximum displacement. And because the y coordinate is equal to the sine of theta, and theta is changing just changing constantly. It's a constant angular speed. Therefore, this thing oscillates as a sine wave, and hence the wave is a sine wave. And so at this position, you can see there's a wavelength. If I take the distance between this point and this point and this point and this point, they're going to be the same. Or where it intersects this dashed line here and then over here. Here it's going down through 0. Here it's going down through 0. So this distance. So these are all the same. That's the wavelength. Now if I just move it just a little bit in time, I still have the same waveform, but it's been moved horizontally. So the question is, how do you write an equation for this situation? It's a function of x, but it's also a function of time. So this is going to blow your mind from, you thought trigonometry was hard, but I'm still going to talk about it because I think it's worth trying to explain it. So in this case, the displacement, which I'll call y, is a function of both x and t. Now the function of x, it's always, so let's just do it as a function of x. So it would be the sine of 2 pi f. So we've seen that term before. It's basically 2 pi f is omega, which is the angular frequency. And then you have t. Okay, so that's, if I look at, where am I got to go back here. If I look at this, it's a sine wave that has a, now you're saying, well, what's the frequency? The frequency is the frequency of this oscillation, even though this thing's not moving at this particular time. You could also write it as, remember, period is equal to 1 over frequency, or frequency is equal to 1 over period. So you could write this as the sine of 2 pi over t times t. So I can put f in the numerator, t in the denominator. And also we have this relationship that v is equal to lambda times f. So you could put it in there in terms of lambda. You could put f instead of f, you could put in v divided by lambda. So that's another way you could put it. Sine of 2 pi f is v divided by lambda t. That'd be another way of representing that. Okay, now if you remember back to pre-calculus again, if you have a sine wave and it's displaced horizontally, so let me get my graphing program out here. Okay, let me just, while we're at this point, I'm going to save this. That's the calculus class. I can get rid of that. Let's go to the graphing program here. So let's plot the sine of x. And we're going to plot the sine of x minus pi over 2. So what we get is we get two sine waves, one that's displaced horizontally from the other. So the basic sine wave is the sine of x. When we subtracted pi over 2, that's a horizontal shift of pi over 2. So the blue curve is to the right, a horizontal shift of pi over 2. So it's the same curve, it's the red curve, except it's moved pi over 2 to the right. And if I plot it the other way, if I do it plus pi over 2, it's going to move to the left. So now this is the peak. This peak has been moved to the left pi over 2 units. So that's your horizontal shift. So what we want to do in our case of our simulation here is we want to have a shift that's a function of time. So let me write that down. So what we want to do is we want to superimpose a horizontal shift that is a function of time. So what do we know? We know in t seconds, it shifts lambda in the x direction. So how do we relate this all together? So this is yeah, I'm trying to remember how to make sure I do this the right way. So let's think about this. So what's happening is this peak is moving to the right, and the speed that this peak is moving is v. Okay. So what we need, I'm probably going to mess this up. So I'm going to write the answer down and I'm going to explain it. So I'm going to write the actual final answer and then we'll figure it out from there so I can explain it. That's the danger with no notes. I could just have all this stuff written down in notes. I wouldn't know anything. This shows that this shows where I don't have everything memorized. Okay. So I'm going to write this result down and we'll figure out why it's true. So y as a function of x and t is equal to some amplitude. I forgot the amplitude here. So we got the amplitude. Now you can either use the sine or the cosine. I chose the sine, so I'm going to stick with it. Sine of omega, which is 2 pi f. Let me just write that as 2 pi f. So it's 2 pi f times x over v minus t. Interesting. It's not exactly it. I would have done, if you switch it the other way, you'd have t minus x over v. Well, what they have is the cosine, so that probably works with the cosine. So I think this is right, except I got to switch these. So you've got t minus x over v. Let's see if they have any other alternative versions of this thing. Yeah, so another way of writing this using the relationships I had, you have the sine of 2 pi f times t minus, yeah, that's not the one I wanted to use. This is fine. So what is this x over v term that I've just calculated? It has to have units of time. And since this is a function of time, you want to have a time minus a shift in time. If you think about velocity is equal to change in position with respect to time, then change in position or time, if you solve for time, is you get delta x over v, which is exactly what we have there. So what this term is doing is oh, I know where I went wrong in this whole thing. Okay, so let me go back and fix it. Sorry about this. This actually should be x. And the reason that should be x is because I was looking at a particular point in time. So this part's x, so it does actually go the other way. So this would be x, and then you'd have x minus this shift, the t part, and the t part is so let me just think about x. X has to be equal to velocity times time. So this has to be, you could have it v times the period, or you could have a sine of 2 pi f times x minus v divided by the frequency. There's all these different ways of kind of writing it in the same arrangement. So what this what this displacement is, this is the shift, the horizontal shift here as a function of time. I'm shifting this equation either to the right as a function of time, and that shift is equal to the velocity of the wave, the speed of the wave times the period of the wave, and that will give you, actually it's not the period of wave, it's just t. Sorry, I got that wrong too. It's just t. Should be, it's still the same units, but it's actually t. So that is correct. So what you get is you get a stationary wave, and then you have the stationary wave moving to the right because I've got a negative sign as a function of time, and it moves equal to the velocity of the wave times the time after your initial time. Yeah, that's correct. So that's what it looks like. It's still a sine wave with a horizontal displacement. In this case, normally in pre-calculus, this was pi over 4, pi over 6, pi over 8, or something like that. Or also notice that's one thing that people always messed up in pre-calculus. So this is a little history pre-calculus thing. So if you had y equals the sine of 2x minus pi over 2, a lot of people would say the x shift is equal to pi over 2. What's wrong with that? You can remember back to pre-calculus, see if Mr. Appel taught you how to do this. Because you think, oh, that's... But look up at the top equation. I said Vt was the horizontal displacement. So you said, well, that's right. But notice how I factored out 2 pi f. So what you do is you factor out the 2 here, so you get the sine of 2 times x minus pi over 4. So this is wrong. The x shift is actually pi over 4. So you always have to have this. If you actually had the equation written in this form, 2 pi f x minus 2 pi f v t, so I'm just multiplying everything by 2 pi f. This would not be the horizontal displacement as a function of time. You've got to factor out whatever the coefficient is in front of x out of both terms. And just from a unit perspective, we didn't really talk about that in pre-calculus, but from a unit perspective, it wouldn't make sense. So this has to have units of meters. Therefore, this shift has to have units of meters. This has to have units of 1 over meters, because the argument of a trig function can never be anything. It has to be unitless. So that's another little fun fact that you don't learn in pre-calculus. Okay, so there's the equation. So let's see if we can think about that actually happening here. So what you've got is you've got this sine wave that has a certain wavelength, and all you're doing is you're just shifting. Let me find the part here. So I'm just shifting that sine wave horizontally as a function of time, but it's it's just a repetitive sine wave. Okay, so that's how you would describe that function. Now, the question is, let me stop this thing, restart. Nope, just stop. Where do I stop this thing? Stop, restart. What if I fix the other end? And instead of oscillating, I'm just going to give it a pulse. So here's the pulse, and I give it a pulse. So there goes the wave. It hits the other side, and it reflects off of the fixed point. And then this is this side's fixed. So then it reflects off of that fixed point. Because there's no friction, it just keeps moving from right to left and then is reflected. Conservation of energy. We can't lose any energy because there's no friction. So this, and let me stop this thing at a particular point. Okay, right there. Okay. So when you're reflecting this thing, you get to this point where there's no displacement. So where's the energy at that point? So let me go over in here and pull this string again. You know, I'm putting the energy in because of the tension in the spring and let go, string in the string. So there goes the energy and it's getting transmitted. In this case, it's dampening out. But you can see the wave, this is just the pulse. This is a pulse right here, right? If I do this, it's not a pulse. This is an oscillating situation. So if I do a pulse, it goes down and it oscillates back pretty fast. So when there is a point where there is no displacement. So where is the energy?
Is it like spring potential energy?
Yeah, there's no spring though. There's no stretch. But I've paused it so you don't see it. So it's in motion. So, you know, what we do is we create spring potential energy by stretching the string originally. But what happens is that when you get to the end and there's one clamped end, and at this particular instant in time, all the energy is in the kinetic energy of the string. And then that kinetic energy of the string is pulling the string down, which then stretches the string. So then you have the string stretched. Let's start it going again here. So then it gets stretched, and there's both potential and kinetic energy involved when the wave is propagating down the string. But right at the end, just as it's in the middle of its reflection, there is no stretch. Well, there is on that side, but on this side there's not. Right there. Yeah. At that point, all the energy is in kinetic energy, but not in spring or elastic potential energy. Okay, so that's what happens if you have a fixed end. Let's see what happens when you have a loose end. We'll restart here. Oh, I got a pulse. Put the pulse in. Okay, so there's the pulse. So the energy being transferred down the string gets to the end, and the little hoop on the other end goes up. And then it reflects down the bottom, and then the hoop goes down. There's no friction between the hoop and the rod. So it still reflects, but it kind of reflects in a different manner. So let's see what happens. So there you're stretching the string. Yeah, there's no point in this one, except maybe over here. Yeah, so it does have this zero stretch condition on the left-hand side, but not on the right-hand side. Well, actually, I'm not sure about that because this hoop is loose. I don't know if it is longer though, so maybe there is stretch in the string. But there probably is. But you can see on the other side here, it does go to a point where, again, there's no stretch in the spring. So so you know, where does that? What's the whole concept there? When we get to sound waves, there's two situations. One which is called a node, and the one's called an antinode. And if you have a solid surface, there's no displacement at a solid surface. So that's kind of a boundary condition. But if you have like a flute, which has two open ends, there is no solid surface. So you end up with different boundary conditions to your sound waves, which can affect how your instrument sounds and the frequencies at which it oscillates. Okay, so there's the pulse. Now what we're going to do is we're going to fix the end, and we're going to oscillate this thing and see what happens. So what we'll do is we get these waves going, and they start to reflect, but then you have the wave coming from the other direction, and they kind of they build on each other, or they cancel each other out, depending upon the frequency. if you change the frequency, you're going to get a different wave behavior. And based upon the tension in the string and the weight per unit, the mass per unit length, what you can end up with is standing waves. What happens with the standing wave is that the wave going in this direction will cancel out at certain locations on this string, and it will enhance at some points. So you'll have some places where they'll double in height, and some places where they won't move at all. And those are important because that's what happens with musical instruments like a guitar. When you pluck a guitar string, it's going to resonate such that you get standing waves. So we demonstrated a standing wave here just a second ago. Where did my string go? This is the you can be the you get the so in this case, the first standing wave is where you get a situation like that. So what's happening is the middle is oscillating a lot, and the ends are not oscillating much at all. And then I said if I did this fast enough, see if I can get it to do it, you'll get some point where, and I may not be able to get it to the exact frequency, but what you'll get is the middle is not moving at all. You'll get that's called an antinode, and then you'll get a bigger oscillation here and a bigger oscillation there. And the frequency at which that particular thing occurs, I don't know how to do this faster. And in between it, just everything cancels each other out and you don't get anything. But we'll wait till next Wednesday. We can easily see what's going on. It's hard to get that to work, and it's hard to get this thing to work. What I could do is possibly start this thing and just slowly increase the frequency and see. And what I'll do is I'll move it, speed it up a little bit. So you can see how this thing starts to bounce around, but it's not really gathering. It kind of goes between low and big. So like I said, I'm going to see if I can do it where it actually reaches some kind of a harmonic type situation. You can sort of see it starts to begin here. That's almost a standing wave, except then it loses it again. It's not quite there. Yeah. So you can kind of see the beginnings of it. Yeah, that lasted for a little while. But what's happening is I'm still inputting energy. Well, that one's getting wild. So that's probably getting closer to the harmonics or the standing waves, but it doesn't last forever. But it probably, if I just left it there, it would go through it and then start getting bigger again. So for a while there, it gets into this harmonic type situation, but because it's not exactly the harmonic frequency, it then dampens out for a little while, kind of loses its organization, but then it'll do this. It should do it all over again. So where the frequencies where this just happens and doesn't stop happening. Now in this case, we're talking about 1, 2, 3, 4, 5. So it's about 70 hertz maybe. The sound waves we'll be looking at, or the waves we'll be looking at, will be actually it won't be too far from 70 hertz. Oh, here it says actually it's only 1 hertz cycles per second. Yeah, so sound waves are going to be at least 60 hertz. So it's going to be happening a lot quicker than this does. So maybe if you do have a slight a small amount of time where it's not oscillating, you barely even notice it. Anyway, so that's, let me go just, now that we've seen that happening. I guess theoretically, if you were at the harmonic, it would just keep getting bigger and bigger and bigger and bigger because you're continuing to put energy in it. You'd have to put a little damping to keep it from going really wild. That one's pretty big. So if you put a little damping in there, it's still going to be a harmonic. It's just not going to be quite as big. Okay. So let's talk about a string. Strings. So the first thing to know is wave speed. What is the speed of wave on a string? Well, and we'll call that V. So V ends up being the square root of F over mu. And F is equal to the tension, which has units of newtons. So it's a force. And mu is the mass per unit length. So that's going to have units of kilograms per meter. And if you plug those units into the equation, you get newtons per kilogram per meter. But a newton is a kilogram mass times acceleration, meters per second squared. So if you replace newton with kilogram meter per second squared, divide by kilogram meter, kilograms per meter, these cancel out. You end up with this meter comes up. If you take the reciprocal of that, you'll get the square root of meters squared per second squared, which is meters per second. So it does work out, at least from a units perspective. So so if I want to increase the wave speed, I increase the tension or I decrease the mass per unit length. So if you have a guitar string, if you want to tune it, to a higher frequency, which is a higher wave speed, then you tighten up the strings. If you want a lower note, you loosen up the strings. If you want a higher note with less tension, you use a lightweight string. So the higher strings are lighter weight. Those are the ones that always break. Your sixth string always breaks before any other string. So you've got 50 sets of 5 strings. I hate to get rid of those because they're good, but you have to give up on it after the first. When you first buy a guitar, you're like, oh, I spent all that money on the strings and one breaks and I got to replace the whole thing. But they don't sell. They don't. I don't think they sell single strings because then the strings wouldn't match, and they're really not that expensive anyway. So I made a big deal of that. Now let's look at a string, and we'll talk about this harmonic situation. So the first harmonic we've already shown is where you have this arrangement, and if you look at the wave length of this particular string, the string oscillating, it's actually only half a wavelength, because if I extended this wave and I put it into this imaginary longer part, this would be one oscillation. This would be one wavelength. So the wavelength, so we're going to say for the first harmonic, that's what this is called. It's the lowest frequency at which you'll get some kind of resonant type behavior. Harmonic. The wavelength is equal to L over, or 2L. Or L is equal to lambda over 2. And then we have this relationship between wave speed, which says the wave speed is equal to lambda times f. Or if we solve for frequency, frequency is equal to V over lambda. So I'm just solving for F. Therefore, frequency is equal to, but lambda is equal to 2L. So I get 1 over 2L times V, where V is equal to the square root of F over mu. So if I have let's say I have a string, my guitar string, and if I find the typical weights and tensions of a guitar string, so let me find that here. So we'll say tension and weights of guitar strings, string tension guide. I guess I'll accept that, whatever that. Well, one thing we need to know is what is the length. So the classical acoustic guitar has a length of 25.5 inches. So we'll need that. So L is 25.5 inches. We'll convert that to meters in a second. Tension. So this is the high string, high E, has a tension of 16.2 pounds. We'll have to convert that to newtons in a second. So F is equal to 16.2 pounds. And the mass per unit length is 0.000382. Well, depends on which one we're dealing with here. Oh, we're dealing with this E string. Is that right? A, B, C. So we got B. Yeah, it's going to be one of the lighter weight strings. And they're doing it pounds per something. Or is this tension? Am I doing tension? I'm going to find another website. I don't like that one. That's tension guides. Let's see. Weight per unit length, or mass per unit length, I guess, really. Mass per unit length. Guitar strings. Oh, there we go. Now, I don't know which ones are which, though. That's for a harp. Oh, there we go. Mass per unit length. Oh. Deriving the formula for mass per unit length. Typical setup of strings, diameter. Well, we could take the diameter and, oh well, I'll find that for next time. We're close enough to the inferior. But what you do is you find the mass per unit length for the strings, and you can just plug into the formula. You can calculate the wave speed by taking the tension in newtons divided by the mass per unit length, kilograms per meter. You'll get the units of velocity, which is meters per second. And then to find the fundamental frequency, you just take 1 over 2L, which is 25 inches. You convert that to meters, and you plug it in. You get a frequency, and that would be the frequency that the string is going to vibrate at. Now, a string ultimately has not just the fundamental frequency, it actually has harmonics, and the harmonics are just multiples of the fundamental. So say the fundamental frequency is 400 hertz, you'll have 2 times the fundamental, which is 800. That's one harmonic. Then you have 3 times the fundamental, 4 times the fundamental, and you get all these different frequencies acting together, which give you a sound that is not just a boring, I think I told you that, my nasal noise is pretty much just one frequency. But if I have a guitar string or a violin string or any stringed instrument, or my deep my deep bass voice, that has a lot of frequencies involved acting together, which give you this unique sound of that particular instrument, whether it's your voice or whether it's another kind of instrument. So that's it for right now. I guess I'm going to let's assign chapter 13 homework, and it be due next Friday because we haven't covered all the material yet, but by Monday we will have. And that way you can start on it if you'd like to. You know how to do about half of the homework.